This is an experimental video. I'm joined today by Lianne, and it's an experiment because it's different to the normal sorts of videos I would make. This is going to be a discussion between the two of us. We have discussions all the time that are very interesting.
We do.
And often I turn those interesting discussions into YouTube videos that I make on my own, which is a sad and lonely thing to do. So we're going to actually just film the discussion this time. As a caveat, when I turn our discussions into YouTube videos, I do lots of research and make sure my facts are straight. So this is going to be a bit looser. Our facts might not be quite right, but the general gist hopefully will be. Anyway, but also please do correct me in the comments, but I will try and figure out after we've filmed this, if anything's terribly wrong, I'll fix it with subtitles or something like that.
Cool.
Anyway, we were going to talk about
gravitational waves.
Gravitational waves.
This is what I want to know about.
It's in the news at the moment, and I was thinking, like, there are a few explanations. There's the stock explanation that a scientist will give on the news, which is really quick, gets it out there, but it's maybe unsatisfying for people who have got a bit more curiosity about it.
That's what I found. I've been reading articles and. It's like I'm kind of getting it, but not quite. There's not enough.
By the way, part of the reason we have interesting conversations is that Lianne has a low threshold for curiosity. As a science presenter, that's brilliant because I'll be like, did you know that water usually boils slightly higher than boiling point? And she'll be like, what?
Can I start by saying what I think they are?
Yeah, great.
Like just based on my,
okay.
and I realise that this is a very okay. Let's start with the space-time continuum.
Okay.
Right.
Yeah.
We're going to imagine it as a tarpaulin.
Okay. Yeah.
Right.
Cool.
And we're going to put a big bowling ball on that tarpaulin.
Yeah.
That bowling ball.
Yeah.
Is for example, Earth.
Okay.
And gravity is crudely the effect that bowling ball has on the tarpaulin. Yeah. So things that approach the kind of.
Let's just describe what happens when the ball goes on the tarpaulin.
Yeah.
Let's call it a rubber sheet instead of tarpaulin.
Okay. Fine. Okay. Yeah, that's better. Rubber's better. It stretches better. Okay, great.
So what happens? So
you get the rubber sheet. You put the bowling ball on, and it kind of sinks in and creates a dip.
Yeah.
In the sheet around the bowling ball.
Link here to a video of that happening. Probably. And
if you drop, I don't know, a marble onto the rubber sheet, then it will fall towards the bowling ball. If you actually kind of throw a marble on at the right angle, it will kind of spin around.
Yeah, because you create a sort of funnel shape like that, so it's going to spin around.
Yeah. And that is a crude way of explaining what gravity actually is.
It's the warping of space-time.
The warping of space-time. Brilliant.
So, by the way, I just to interject, I really like that as a visual aid. It's very simple. What I don't like about it is it's an explanation of gravity that requires gravity. Because you've got this rubber sheet and you put a ball on it. The ball is pulled down by gravity, and the balls that you then put on it are pulled down by gravity.
Okay, fair enough. However, I mean, it's quite difficult to do an experiment to demonstrate gravity in a place with no gravity.
No, it is. It is.
How do you know?
Well, I don't know.
You want these experiments to be done.
You wouldn't. But yeah. So whereas the warping of space-time is more like. A straight line now becomes a curved line. Do you see what I mean? So an object that curves around the Earth, in some senses, isn't accelerating, even though it's changing direction.
Okay.
Anyway, it's a nice visualization, but I think it skirts over what's really going on a little bit. Oh, I did find a really good video of someone demonstrating how curved space leads to gravity. He built this amazing thing. I'll see if I can find a link and put that in there as well. So that's not gravity waves. That's
okay. So this is just I don't know if I'm right here. So you can tell me if I'm not.
Yeah.
But my thinking is that a gravitational wave. So I gather it's when there's a collision of two. Colossal. I'm going to say objects, but I don't mean objects because what I'm thinking of here is black holes.
Okay.
Two black holes collide.
A black hole is an object, I guess.
Okay, great. Black hole's an object.
An object. Some strange properties.
D object. Two D objects collide, and the force of the collision sends ripples out in the fabric of space-time.
Yeah, okay.
And those ripples are gravitational waves?
It's not bad. It's not bad. Yes, except that, you know, if we were to walk around each other, we would create gravitational waves. So it's just that they're just tiny, right?
What? Yeah, so the ones that are created by the collision of the two black holes would be so big that you can actually detect them.
Yeah.
Whereas the ones that we create are teeny.
Yeah. So, okay, the way to think about gravitational waves, there's a couple of nice ways. One way is to think about it in terms of electricity and magnetism, and using that as an analogy. Okay, so an electron has an electric field. Yeah? Is that an idea you're familiar with? Yeah. All that means is it has an area of influence around it. Mm-hmm. So it influences charged particles that are near it.
Yeah.
So we call that its electric field. Mm-hmm. Another way of thinking about that, instead of saying an electron has an electric field, you say there is an electric field, there is one electric field that permeates the universe, and electrons cause a disturbance in the field.
Okay, I like that.
Okay.
Right.
So an electron is sitting in this field, and it causes a lump, if you like, in the field.
Okay.
And so
that's nice.
It's nice.
That's really nice. That's really nice.
So what happens when you move the electron? The field moves as well.
Yeah.
Right? The field doesn't move instantaneously. It moves at the speed of light.
What? Oh.
Yeah. So imagine I've got an electron here. And you're really far away, but you can feel the force of the electron, right? And then I move the electron over here, right?
Yeah.
And you can detect that the electron has moved.
Right.
Suppose the electron's moved away from you.
Okay.
You can detect that it's moved away from you because the force got weaker, right? But you don't detect it at the moment the electron moves. You detect it
the speed of light.
At the speed of light, so the time it takes for the change in the disturbance in the field to get to you.
Yeah.
Okay? So what happens if I take that electron now and I move it backwards and forwards like that?
Oh.
So that change in the field, that disturbance in the field, is kind of it's at this point here it's getting bigger and smaller, bigger and smaller, bigger and smaller, right? But that disturbance then travels through space at the speed of light. Okay, but here's the cool thing: when you disturb an electron like that, it doesn't just create a disturbance in the electric field that permeates the universe. It also causes a disturbance in the magnetic field that permeates the universe. And that disturbance, those waves that travel away from it, they travel in a packet of waves, and that packet is a photon.
Right.
A photon is a disturbance in the electric field and the magnetic field
at the same time.
Yeah.
Right.
And they travel away from electrons when you jiggle them. So.
Okay. No, I'm yet to understand how this relates to gravitational waves, but
so,
we'll get there.
So let's think about. It'd be good to talk about Einstein's general theory of relativity and theories in general, because. So Einstein came up with this theory of general relativity, which describes gravity. Mm-hmm. But we already had a theory of gravity, which is Newton's universal law of gravity.
Right.
And Newton's universal law of gravity describes gravity really well. And so the reason it's called the universal law of gravity is because, and this was his genius, he realised that an apple falls to the ground for the same reason that a planet orbits the sun.
Right, yes.
So you call it universal because it's everywhere, right? And that's great. So you've got a theory that describes everything. Mm-hmm. Brilliant. But when you have a scientific theory and it works and it describes everything, you don't just stop at that point.
Yeah.
What you do is, and this is in an ideal world, this is like an idealized scientist. This is what a perfect scientist would do. They would then say, okay, I'm now going to try and disprove my theory.
Right.
Okay. So a good theory is one that is disprovable. Right? So what we say is a good theory in physics is falsifiable. What that means is the theory makes predictions that we can test and hopefully prove to be wrong. And if we find out that we can't disprove the theory, then that theory is now even stronger than it was before.
Right.
Okay?
Okay.
So Newton's theory of gravity explains everything we see, but can we use the mathematics to come up with a description that we haven't seen yet, and then try and look for that thing? According to Newton's theory of gravity, if you have a planet which is in an elliptical orbit, so imagine you've got the sun here, and you've got a planet which is going like that, you know, like that, an elliptical orbit like that. That ellipse won't be stationary, but it will kind of slowly move around like that.
This is according to
Newton.
Right.
At a certain speed, and it's called a precession, right? And so Mercury has an elliptical orbit like this, and the ellipse precesses around.
Right.
But it doesn't precess at the right speed. So, by testing Newton's theory of gravity, we find out that it doesn't describe something.
Right.
So maybe there's a problem. It's called the anomalous precession of Mercury. Oh. Einstein came up with the general relativity theory, which describes gravity, and it correctly describes the speed of Mercury's precession around the sun.
Nice work, Einstein.
Great, that's really good.
Okay.
But is there something else in the theory that we can use to now continue to test it, to try and disprove the theory of relativity, general relativity? And one of the predictions of Einstein's theory of general relativity is gravitational waves. So looking for gravitational waves is a really important thing to do in science, because you're probing, you're really figuring out, is this theory definitely true?
Right.
And the answer is never yes, but
it's okay.
It's
We've
more
proven one more part of the theory.
Yeah.
It's even more likely to be true.
yeah, exactly.
Okay.
So that's why we've been looking for gravitational waves, and that's why it's so important that we found them.
Right. We still haven't got to what they are.
No, we haven't. So in Newton's theory of gravity, you feel the effects of gravity instantaneously, right?
Right.
So if the sun were to suddenly appear, you would instantly be attracted to it, no matter how far away you are.
And yes, I know that that we now know that gravity travels at the speed of light, or the effects of gravity are felt at the speed of light.
Yeah. Well, this is one of the predictions of general relativity. So Einstein's theory of relativity, gravity isn't instantaneous. It travels at the speed of light.
Yeah.
So in the same way as an electron is a disturbance in the electric field that permeates the universe, a massive object creates a disturbance in the gravitational field that permeates the universe.
Einstein's a G. Sorry.
Yeah. I know.
It's just hitting me again. But anyway, go on.
Uppercase.
Yeah.
He's not. I mean, uppercase G, not lowercase g. But so for example, do you know why he got his Nobel Prize?
No.
What field was it in?
I know that it's not what I would expect.
Yeah.
Well, what was it?
He got it for quantum mechanics. So the two biggest theories in modern physics, relativity and quantum mechanics, he was a big deal in both of them.
Wow.
So, what were we talking about?
Gravitational waves.
You can either think of a massive object as having a gravitational field, or you can think of it as a disturbance in the gravitational field that permeates the universe.
Yes.
Except that, instead of it being the gravitational field that permeates the universe, it's the fabric of space-time itself. Yeah. So in the same way that when you wiggle an electron, it produces disturbances in the electric field that permeate through space at the speed of light, when you wiggle a massive object, it produces permutations in space-time that travel at the speed of light.
In the same way, right.
Yeah. So if I had a massive object and I just moved it backwards and forwards, that would produce gravitational waves in the same way that you would get electric waves when you wiggle an electron.
Right.
Does that make sense?
Yeah.
So there you go, gravitational waves. Is that satisfying? Or
it's satisfying. There's still some stuff I don't understand.
Yeah.
So one of the articles I was reading was talking about the scientists who were looking for the gravitational waves listening to two black holes circling each other for 20 millionths of a second or something.
Yeah.
Like how are they detecting it? What are they listening to? What does this mean? What's going on?
So imagine you want to detect gravitational waves.
Yeah.
Okay. And remember, a gravitational wave is a disturbance in space-time itself.
Yeah.
So it might be a lengthening and a contracting,
Of space-time.
Yeah. So what you do is you get like a rod of metal, right? And there's waves. Hopefully there's waves hitting it from this this binary black hole that's spinning around itself, right? And then you measure it, and is it getting bigger and smaller, right?
The rod.
Yeah. Is that going to work? Is that going to work?
What is measuring the rod?
Yeah.
Well, I from the way you're saying it, I think no.
No,
I don't know why.
Well, because your ruler's going to be doing the same thing.
Right. Yeah. Obviously. Okay.
So.
Oh, good. Yes, I like that. Oh, tricky. So how do you get around this?
You use light. Because light always travels at the speed of light. So what you do is you send a laser light, down a massive tunnel.
Yeah.
And then when it comes back, what you could do is time how long it takes. Right? Because if space stretched, then it would take longer because the speed of light's always constant.
The speed of light's always constant, but of course it can... Yeah, okay. Right.
So that's the one thing that we're sure about. Is that the speed of light is constant. So if space contracts, it will take longer to get there and
because
back.
The speed.
But that's such a hard thing to measure, that difference in timing. It would be impossible, right? So what you do instead is you use something called interference. So if I send light, if I use a special thing to split the light in two. Right, so half the light goes that way.
When you say half the light, you're saying half a photon, or?
Well, yeah, because it's quantum mechanics. So it's a bit like a double slit experiment where the photon goes down both paths.
Oh God, I love that.
Yeah,
That's
another video, isn't it? But
yeah.
Anyway. So you split the light in two. So you've got a beam coming in here. Half the beam goes that way. Half the beam goes perpendicular, that way, right? And then they come back, right? And you've made it so.
Oh, yeah. Okay, on.
And then when they come back, you've arranged it so that the distance they have to travel means that when they get back, and remember light travels as a wave, you do it so that the peak of the wave coming this way exactly matches with the trough of a wave coming this way.
Right.
So they cancel each other out and you get no light. That's destructive interference. Right? Now, this gravitational wave that comes in, suppose it's coming from directly above, right? It has the effect of stretching in this direction and shrinking in this direction.
Right.
So what that means is a teeny tiny change in how far this light has to travel versus how far this light has to travel. And it could be, the width of a wavelength of light.
Yeah.
Which is like hundreds of nanometers or whatever. Or what, it depends on the laser you're using, obviously. You will go from having destructive interference where a peak meets a trough to where a peak meets a peak.
Yeah. So then you get light. So when you see light, you're like, hey, presto, we've had a gravitational wave. Yeah.
Except that, because of like seismic things, you're if you've got a mirror that's miles away. I mean, this is LIGO, by the way. This is the name of the experiment. You've got, you'll have like seismic shifts, which mean that that distance is changing anyway. So you get loads and loads of noise, okay? So you have to try and find this weak signal in loads of noise. And what they did was they built a LIGO at one side of the US and a LIGO at the other side of the US, where the noise is different, and they can somehow pick out the signal from the noise like that. And that's what they did. And that's how they discovered the gravitational waves.
Okay, so should I sum up what I've understood?
Go on.
A gravitational wave is a disturbance in the fabric of space-time itself. Now, gravitational waves are caused by the interaction or the acceleration of any sort of object.
Yeah.
But they're usually so tiny that you wouldn't be able to detect them. So the gravitational waves that have been detected by LIGO.
I say LIGO, but I
say potato. What do you say, potato?
I also say potato.
Oh,
so I don't know if that's
tomato.
I say tomato.
Okay, there you go. So the gravitational waves that have been detected by...
Let's call the whole thing off.
What? The gravitational wave detected by LIGO were caused by the acceleration, and I thought the collision of two black holes.
Yeah, because the collision involves it. Like when they finally collide, they're just going so fast and producing such mad waves.
Oh, I see. So it's not. It's not like. So in my mind, it was like they collide. There's this massive like, and then that sends like massive waves out across the fabric of space-time.
It's not. No.
Okay.
But brilliantly, as they got closer, they spun faster and faster and faster. So the frequency of the waves they detected got faster and faster and faster until they
So that's what they're saying when they said they listened to these waves.
Yeah.
These black holes circling each other.
Yeah. Where were we?
We were summing up. Should we maybe explain?
This is Lyra.
This is Lyra. She woke up from her nap, so she has come to help. Any object that is accelerating through space-time will create a gravitational wave.
Not any object, but acceleration is a requirement.
Okay, so what objects might not?
For
example?
A spherical object won't. So a spherical object that's spinning, should I say?
That is a no.
So imagine if you had a ball bobbing up and down in a pond and you span the ball. Mm-hmm. If you did it just right, you wouldn't see waves coming off. But if you had a dumbbell and you span it in the pool, every time a dumbbell swept around,
it creates waves.
Create a ripple.
Okay. That would work on my tarpaulin, in my rubber sheet analogy as well.
It would.
Which I still think is really rather good.
Yeah, okay, fine. So, let's go with that. So, if you span a heavy ball on your rubber sheet, you wouldn't get waves. But if you span a dumbbell on the rubber sheet, there's actually 3 clouds. 1, 2, 3. If you span a dumbbell on the sheet, you would get ripples spreading out towards the...
I like the way that I can visualise that. That works for me. So most objects accelerating through space, time, apart from spherical objects, for example.
And cylindrical objects.
So, almost all objects, as they accelerate through space-time, will create gravitational waves.
Yes.
However, in most cases, those gravitational waves are so very tiny that they are impossible for us to detect at the moment.
Yeah.
So the gravitational waves that were detected by LIGO were created by 2 black holes that were in the process of colliding with one another. And in that process, they were spinning around each other really, really fast. Kind of like the 2 dumbbells that you described.
Yeah. Another way of thinking about it is... so Einstein's theory of general relativity is a mathematical description. So it's a theory which is like, it's got a lot of hard equations. And these equations are really, really tough to solve. But what we hope is that our universe is a solution to that equation. In fact, you can even think of it as like...
Wait.
So, I know, it's nice, yeah. But even like, I suppose, you might think, okay, the Earth going around the sun, is that a solution to Einstein's equations of general relativity? And what we find for the observation is that it is. So if I could come up with an equation for how a guitar string moves, when I pluck the guitar string, it will move in all sorts of ways, but the way that it moves will be a solution to that equation. Okay? And in the same way, Einstein's equations of general relativity are general, but solutions to those equations describe particular things, which is where the idea of a wormhole comes from. We don't know if wormholes exist, but we know that wormholes are a solution to Einstein's theory of relativity.
Can we detect wormholes? Like, is that something that we could... Are we looking for them?
We should be able to, and I don't know if we are looking. But we should...
I mean, can we start looking? If no one else is. You see one over there?
I haven't seen one out there, but... Can you... Well, we're blocked by the neighbours there. But...
My eyes aren't that good, actually.
So maybe they don't exist. But anyway, they are allowed by Einstein's theory of general relativity. So I hope you enjoyed this video as well. I hope you enjoyed the format of it. If you did, let us know in the comments. And we'll see you next time. Bye!
Bye!
Want to say goodbye?
Can you say LIGO?
That's the sound of a lion.
Can you say photon? Yes, that is the photons coming out of the light.
Yeah.
She's very clever.
She's very advanced. Okay.